Hi students, welcome back to C level physics. All the best for our tomorrow's physics IPA exam. So read thoroughly and write your exam very cool and calm. So in this video, I would like to explain potential energy and kinetic energy of simple harmonic oscillator. Right? You know, potential energy. What is meant by potential energy? During the oscillation of the particle, its position changes. See, here it is x equal to 0, here it is x equal to plus a, here it is x equal to minus a like that. So during the oscillation on either side of the main position, its position changes continuously with the time. So at different positions, it possesses different potential energy, right? Because of its position. In the same way, its speed also changes. At mean position, speed is maximum. At extreme position, speed minimum, that is 0 on either extreme positions, right? In between, it is between maximum and minimum. So here, with respect to position otherwise time, speed also changes. So due to motion, it possesses kinetic energy. Due to change in position, it possesses potential energy. That's how during simple harmonic motion, a simple harmonic oscillator or particle possesses both P and K, both potential energy as well as kinetic energy. So the sum of P and Ke is known to be mechanical energy. Mechanical energy. Alright. Now let us see. Mechanical energy. What is mechanical energy? Total mechanical energy. That is sum of kinetic energy plus potential energy. U stands for potential energy. Ke stands for kinetic energy. TME stands for total mechanical energy. What is the valid expression for SHM? At t equal to 0, if it passes through mean position rightwards, that is at t equal to 0, if x equal to 0 is the position and moving positive x direction, then what is the valid equation for x? That is x equal to a sine omega t. Omega t. That is omega in the sense a sine 2 pi by capital T into small t. Now what is the speed here? On differentiating will have, what is the form? V equal to a omega cos omega t. That is omega into a cos omega t. That is omega into a cos 2 pi by capital T into small t. Right? Okay. So we have another form also. On extending cos square t, cos 2 pi by t into t, in terms of 1 minus sin square theta, we can have omega into root over a square minus x square also. So here for speed we have two forms. This is one form, this is another form. Right? Cos 2 pi by t. Cos 2 pi by capital T into t. Right? So here kinetic energy changes, potential energy also changes during oscillation. But the sum of P plus Ke is constant. Why? Because total energy is conserved. Even though individually kinetic energy and potential energy changes with the position of time, but the sum of these two, that is total mechanical energy, remains constant, that is conserved. Now let us see how kinetic energy of simple harmonic oscillator varies with the position as well as time. Now kinetic energy K. So what is the expression for kinetic energy? Kinetic energy equal to of mp square. That is, see here we have two forms for speed. V equal to this one, omega into root over a square minus x square. See, on squaring, v square in the sense omega square of a square minus x square. That is of m v square, omega square into a square minus x square. That also equal to m omega square in the sense k of k into a square minus x square. Of k a square minus x square also. See another form. If we take v as omega into a into cos 2 pi by t into t, that is half into m into v square, take this form, that is omega square into a square into cos square 2 pi by capital T into small t, like this. Right? So again, also equal to m omega square in the sense k, that is of k a square cos square 2 pi by capital D into small d. See, this is the form. So this is in terms of time, variation of kinetic energy with the time. This is what variation of same kinetic energy with the position. So that's how we can have two formulas or two expressions for kinetic energy. One is in terms of time, another one is in terms of position, right? Now let us see how kinetic energy varies with the time. Means at different instants, how what is the value for kinetic energy during its oscillation. Okay. Now let us see first point. First point, that is at t equal 0. At t equal 0, see this what mean position. X equal 0 is the position of the particle. X equal to 0 at t equal to 0. At t equal to 0, let x equal to 0 be the position of the particle. That is, particle is at its mean position and moving in positive x direction. Now, what is the phase acquired at this instant, initial instant 0? No phase acquired, right? Now, what is the kinetic energy here? The kinetic energy equal to at t equal to, substitute here t equal to 0. T 0 in the sense cos square 0. That is, cos 0 means what? 1 square. That is 1 into half k square. Half k square. Half k square. That is maximum kinetic energy. Maximum. Maximum. Why? Because cos square value is 1 in the sense maximum. That is 1 into half k square. Maximum kinetic energy at mean position. Right? If I take variation like this, see, variation like this. See, this is what time versus kinetic energy. Time versus kinetic energy. At t equal to 0, what is the value of kinetic energy? Maximum. So this is what maximum value. Now at t equal to t by 4, that is after completion of 1/4 of oscillation, what is the time taken? T equal to 1/4 of time period. That is like this. See, at t equal to t by 4, definitely particle, see somewhere here at right extreme position. X equal to plus a is the position of the particle, right? Particle lies somewhere here. Now what is the phase acquired here? Phase equal to pi by 2. From mean position to extreme, it acquires pi by 2 phase angle. Now kinetic energy, substitute here. If we take t equal to t by 4, somewhere here t equal to small t equal to t by 4, t cancel, 2 pi. See here cos square 2 pi by capital D into small d in the sense t by 4, that is t cancel, 2 cancel, pi by 2, cos square pi by 2, 0. So 0 into something, 0. So what is the kinetic energy here? 0. Here it is maximum, here it is 0. So kinetic energy gradually reduces and becomes 0 here. This is what? T by 4. T by 4. Okay, next. After reaching positive extreme position in the right side, again retraces and reaches mean position once again like this. Once again, mean position. See here, this is what mean position. Particle again reaches mean position like this. See, this is what mean position. Somewhere here below the point here. So and enters in negative x direction. So at t equal to t by 2. See here, 1/4 of oscillation again 1/4. 1/4 plus 1/4. That is 1/4 plus 1/4. So half of the oscillation is said to be completed. So at t equal to t by 2, what is the phase acquired here? Phase equal to pi by 2 plus pi by 2. That is pi. Now kinetic energy once again. If I substitute t by 2 here, tt. See, cos square 2 pi by capital D into small t means what? T by 2. T cancel, 2 cancel, cos square pi. That is cos pi minus 1 whole square. That is minus 1 whole square. 1. 1 into half k square. Half k square. Again kinetic energy max. Half k square. See, kinetic energy never be negative. Always positive. It may be 0 or positive, but never be negative. Why? Because here v square is there. V square of m v square. If v is negative, on squaring will get positive again. Mass never be negative. So therefore, plus into plus into plus, always positive, right? So this is what. Now, till now, half of the oscillation is said to be completed, right? Right. So again, kinetic energy maximum. So from 0 again, kinetic energy increases and becomes maximum, reaches its peak value like this. Okay. Now what is the instant here? T equal to T by 2. Right. So next, three within completion of 3/4 of oscillation. Now what is the position part here? It reaches negative extreme position like this. Negative extreme position. It reaches this position. Extreme position on the negative side. Right? It reaches here. What is the time taken here? T equal to 3T by 4. 3/4 of oscillation is said to be completed. Now what is the phase required here? Phase equal to 3 pi by 2. So at extreme position, once again kinetic energy is 0. Otherwise, if you put T equal to 3T by 4, again we will have 0. 0 into something, 0. That is kinetic energy is again 0. Again 0. Means kinetic energy gradually decreases and becomes 0 like this. I am changing the ink like this. So 0. What is the time here? 3T by 4. Okay. Again, it retraces and once again passes through main position. Ultimately, passes through main position. See here, once again particle reaches to its main position and enters in the right side. That is in the positive x direction. So what is the instant here? T equal to time period. Now what is the phase angle here? 2 pi. What is the kinetic energy here? If I take T equal to capital T cancel, cos square 2 pi. That is 1. So 1 into half k square. Once again half k. So kinetic energy equal to maximum, that is half k a square. So half k is. So once again kinetic energy becomes maximum like this. Reaches its maximum value. See here, this is what. So from here to there in black in color, but here to there blue in color like. Why to take like that? See here, within one oscillation, that is within completion of one oscillation, kinetic energy it reaches twice maximum to its. See here kinetic energy is maximum. Here also one more time. Once here maximum, one more time here maximum. Right? So within one oscillation, kinetic energy becomes, it reaches twice to its maximum value. It reaches twice to its maximum value. That's why what I am saying here, the frequency of oscillation of kinetic energy is 2 omega. So frequency is said to be, here it is, frequency is said to be 2 omega. So time period is said to be 2 pi by 2 omega. That is pi by omega. So frequency of oscillation of kinetic energy equal to omega. Time period is said to be 2 pi by 2 omega. That is pi by omega. But if you take x, either x or v or acceleration, so these are all simple harmonic. These are the relations or mathematical expressions related to simple harmonic motion. Now what is the frequency of x here? Omega. Implies time period is 2 pi by omega. Here, what is the frequency of velocity here? Omega. Time period 2 pi by omega. Means velocity oscillates with the frequency of omega with the time period of 2 pi by omega. Similarly, displacement oscillates with the frequency, angular frequency omega and time period 2 pi by omega. Similarly, acceleration. Acceleration also. See, acceleration equal to, on differentiating this one, minus omega square into a sin 2 pi by capital into t. Here also, see here what is the phase angle here? Omega t, that is 2 pi by t into t. So what is the frequency of oscillation, acceleration here? Omega 1. Time period 2 pi by t. T equal to 2 pi by omega 1. Here also, what is the frequency of oscillation, velocity? Omega. Otherwise, time period is 2 pi by omega. Here also, what is the frequency of oscillation of displacement? That is omega. Otherwise, time period equal to 2 pi by omega. See here, in the case of first expression, see x versus time, see a sine function like this. In the case of velocity, cos function, cosine means like this. So velocity versus time. In case of acceleration, In case of acceleration, simply invert the loops here. That is, crust goes into trough, trough goes into crust. See here, negative sign is there between these two, but here it is sine function, here also sine function. So negative sign, positive cosine. Now see, here it is plus, here it is minus, here it is plus, here it is minus, like here it is minus, here it is plus. Okay, so here it is plus, otherwise see here, not here, here it is minus, here it is plus. See, all the three factors, displacement, velocity and acceleration, all the three parameters, or all the three factors reaches twice to their maximum values within one oscillation here. Here see, once displacement maximum here, one more time maximum here. But see, here it is positive, here it is negative. So that's why this is said to be half of the loop only. So one positive and one negative is collectively said to be complete cycle. Here also, see, acceleration is maximum once here, one more time here. But here it is negative, here it is positive. So both segments collectively known to be one complete cycle, right? Within one oscillation, here also acceleration reaches its twice to its maximum value. In the same way, as far as velocity is concerned, here also velocity becomes maximum once here, one more time here. But here it is negative, here it is positive. That's why from here to there half of the cycle, from here to there half of the cycle. So altogether one cycle. Here also, from here to there half of the cycle, here to there half of the cycle. Altogether one cycle. Here also, this is the half of the cycle, this is the half of the cycle. Altogether one cycle. But here also kinetic energy reaches twice to its maximum value within one oscillation. See here, once here, one more time here. Once here, one more time here. But both values are above the time axis only. Why? Because both are positive. Here positive, negative. Here negative, positive. Here negative, positive. But here also kinetic energy reaches twice to its maximum value. But both values are on the same side only, positive side only. That's why from here to there, one cycle, that to be one cycle. From here to there, one more cycle. So that's why the frequency of oscillation of kinetic energy is said to be twice that of any of x or v or a. Here it is, what is the frequency of x? Omega. Here it is, what is the frequency of oscillation of v? Omega. What is the frequency of oscillation of acceleration? Omega. But here, what is the frequency of kinetic energy of oscillation? That is 2 omega. That is 2 omega, not omega, 2 omega. Very, very crucial point, very important point. That is 2 omega, not omega. That is 2 pi by 2 omega equal to pi by omega. That's what time period. That's what time period. So from here to there, one cycle. From here to there, one cycle. So one more cycle. So 2 cycles within one oscillation. 2 cycles within one oscillation. That's why frequency of oscillation of kinetic energy is 2 omega. It's not omega. That is twice that of any of x or v or a. Right? That is the beauty of physics. That's why you are going to love physics. Right? So next one. So kinetic energy is completed. Now it's the turn of potential energy. It's the turn of potential energy. Potential energy. Potential energy. That is U. Potential energy U. Right? So what is meant by potential energy? Energy possessed by a body or particle by virtue of its position or state or configuration. So during the oscillation of the particle, its position changes, otherwise its configuration with respect to surroundings changes, otherwise its state changes. So that's why it possesses potential energy. But that potential energy is not constant during its oscillation, right? So you see here, this is the mean position. For example, particle is going to deviate from its main position, that is in the right side of the main position. At a given instant, let it be the position of the particle. So what is the displacement here? That is x. Now immediately it is acted upon by some restoring force, which tries to bring the particle again to its previous position. That's why F equal, see the direction of restoring force, that is F equal minus kx. Right? See, these two are directed opposite to each other. See, this arrow mark corresponds to force, this arrow mark corresponds to displacement. If at all it is further displaced through a small amount dx, this restoring force does some work on the particle. What is that work? Work done by that restoring force for the small displacement differential form, take into differential form, that is dw, by conservative force. Work done by conservative force. Why it is conservative force here? F equal to path independent. It doesn't depend upon direction of motion. Whether a particle is in the right side of the main position, otherwise left side of the main position, otherwise as it is moving right side or left side, what irrespective of direction of motion. What is the direction of restoring force? Always towards main position. That's why work done by this force is independent of path followed by the particle. Right? That's why it is said to be conservative force. So work done by this conservative force equal to, we know that negative of change in potential energy du implies du equal to minus dw c. Now what is dw? Work done by conservative force equal to f bar dot s bar, that is du equal to minus f bar dot dx bar, displacement dx, right? So du equal to minus f bar dot dx bar, f bar dot dx bar, see f bar here dx. Now if you want to get variations in large scale, how to integrate the given expression on either side, that is integral du equal to minus integral f bar dot dx. What are the limits here? See here, position changed from x equal to 0 to x, so 0 to x. At x equal to 0, what is the potential energy here? Let it be u naught. Let it be u naught. At given position x, what is the potential energy? Let it be u. Why it is u naught? Why it is not the 0? Usually we are going to take u, potential energy, at 0 at main position, but it doesn't. It is not always right. Why? Because the minimum potential energy may be 0, otherwise may not be 0. It's a matter of choice of reference level. Why? Because see here, one cradle is going to oscillate, otherwise one simple band is going to oscillate, such that its main position is just above the reference level, like this, just above the reference level. See, this is what reference level, otherwise ground, for example. What is this position x equal to 0? So u at x equal to 0 equal to 0. Why? Because here this is the reference level in the sense the level at which potential energy is to be taken as 0. So it's fully our choice. So therefore at this position potential energy equal to minimum, that is 0. The same reference level is taken somewhere here, for example, see somewhere here like this, reference level like this. In this case, the lowest position of the particle, that is mean position, is at some height above the reference level. So if you take this line as the reference, in this case for the same oscillator, the least potential energy at its main position can't be 0, may not be 0. That is at this position u at x equal to 0 is not equal to 0. So for the same oscillator, for the same position, here potential energy at main position is 0, but here potential energy at the same position for the same oscillator not equal to 0. So that's what I'm saying. So the least potential energy, otherwise minimum potential energy at its main position, it may be 0, otherwise may not be 0. It depends upon the choice of reference level taken. Okay. So that's why I'm taking minimum potential energy at main position to be u naught. Okay. Now on extending, see here integral du under limits u naught to u equal to minus a bar dot b bar, means mod a bar mod b bar cos theta, that is integral 0 to x mod a bar mod b bar cos theta. Theta means what? These two directed opposite to each other, force and displacement. That's why 180 degrees. Cos 180. that is cos 180 minus or minus plus minus 1 into minus plus, that is positive plus integral 0 to x mod f bar. What is f bar? Minus k into x bar. And taking modulus kx, it becomes kx. So kx into integral dx, mod dx bar in the sense dx only. Kx into dx. Here integral du under limits u0 to u0 to u. So on extending, what will you get here? On extending, see, on extending, upper limit minus lower limit, that is u minus u0 equal to k is kept outside, integral x dx in the sense x square by 2 limits 0 to x, that is u minus u0 equal of k x square minus j, that is half k x square. So u equal to u0 plus of k x square, u0 plus of k x square. This is what variation of potential energy with position x. Here u0 plus of k x square, right? Now, when the potential energy is minimum, when it is maximum, let us examine. At x equal to 0, what is the least value of potential energy? U at x equal to 0, that is u at main position equal to what? u0. X equal to 0 means we left with u0. Means at minimum, at main position it possesses some minimum potential energy. At u at x equal to plus or minus a, that is u0 plus of k a square, of k a square. So of k a square, right? So see the variation here, how it varies graphically. We can take like this. See, at the main position it possesses some potential energy somewhere here. See, this is what some potential energy. So total energy versus position, potential energy, otherwise potential energy versus x. See, this is what x equal to 0. At x equal to 0, it possesses some minimum potential energy. It is not equal to 0 here. It is not equal to 0. For this relation, u0 is not equal to 0. So this corresponds to what? u0. Minimum potential energy at its main position. Now it is what? These two positions are nothing but x equal to plus a right extreme position, potential energy maximum. At left extreme position also potential energy is maximum, like this. So x equal to minus a, right? Now you can overlap kinetic energy, variation of kinetic energy. We can show the variation of kinetic energy on the same graph like this. See, at mean position kinetic energy is maximum, like this, right? At extreme positions kinetic energy is minimum, like this. Okay, see, like this. At mean position kinetic energy is maximum, at extreme positions kinetic energy is minimum, like this, right? So at extreme positions kinetic energy minimum, at mean position kinetic energy maximum. Now see, this is what. Now you can take either u or k. So this is what? Variation of potential energy. Now this is what? Variation of kinetic energy. Now this is what? See here, this is what? See, total mechanical energy. Now see this segment, this intersection, otherwise here it is u0, here also u0. In the case of in which potential energy is not zero at its main position, in this case, especially in this case. See, this is kinetic energy, this is for potential energy, this is for total mechanical energy. Remains constant from here to there. So at any position in between plus or minus amplitude. So at any position total mechanical energy remains constant, but kinetic energy, potential energy as well as kinetic energy changes, but total mechanical energy remains constant. Here it is, interception is potential, the value of potential energy at mean position, right? That is the variation, right? So if I take u naught as 0 in the same expression, suppose as I explained in the previous case, whenever one simple pendulum oscillates such that its mean position is just above the reference level, in that case u naught is 0. So if I take u naught as 0, then what will you get here? U naught as 0. See, this is what number 1, for example. 1 implies, see, if u at x equal to 0, that is u naught is 0, in that case 1 implies the relation reduced to u equal to half k x square, right? Half k x square. So in that case, how it varies? See, like this. How it varies? Potential energy versus position. So at the mean position, it doesn't possess any, it don't have any potential energy. So this curve goes through mean position, goes through origin like this, right? This is the variation of potential energy in the case of u at x equal to 0 is 0, right? So this is what usually x equal to plus a. So this is what the position with x equal to minus a. This is what x equal to minus a. This is what x equal to 0, right? So this curve corresponds to potential energy, right? If I take the variation of kinetic energy in this case on the same graph, kinetic energy becomes maximum at mean position and minimum at that is 0 at extreme positions like this. See, graph goes like this, right? So this is what for kinetic energy. So kinetic energy. Now what is the total energy? How can you represent total energy here? The total energy usually remains constant at any position like this, remains constant like this. This is what potential energy. Now here it is total energy like this, total mechanical energy. See, throughout the oscillation, total mechanical energy remains constant, even though both potential energy as well as kinetic energy changes individually, but the total mechanical energy remains constant. That's how we can have variation of potential energy and kinetic energy with the position, right? Now a small numerical, for example, in SHM, small numerical, in SHM, total mechanical energy equal to 500 joules. Total mechanical energy of the oscillator is 500 joules. And U at question number A1, U at x equal to 0, that is energy at mean position is not equal to, that is 100 joules, for example. 100 joules. Find A, U at otherwise K at kinetic energy at x equal to 0, B kinetic energy at x equal to plus or minus a, and C potential energy at x equal to plus or minus a. Now see, so in all the three cases, whatever the position of the particle during its oscillation, total mechanical energy remains constant at x equal to 0 or at x equal to plus or minus a, otherwise at any point between minus a and plus a. So I am taking to find K at x equal to 0, total question number A, total mechanical energy at any position equal to sum of P and K at the same position, that is kinetic energy at x equal to 0 plus potential energy at x equal to 0. What is the total mechanical energy? That is 500 joules at any position, that is 500 joules equal to Ke at x equal to 0 is unknown, plus U at x equal to 0, what is the value? 100 joules. That is, what is the kinetic energy at x equal to 0? Ke at x equal to 0 equal to 500 minus 100, that is 400 joules. Now question number B, What is kinetic energy at x equal plus or minus a? So directly we are very much familiar that speed at extreme positions is 0. That's why kinetic energy definitely 0. That is kinetic energy at so direct answer, that is kinetic energy at x equal to plus or minus a equal to 0 since speed equal to 0. Now question number C, potential energy at extreme positions, that is U, total mechanical energy at extreme position equal to total mechanical energy at extreme equal to kinetic energy at x equal to plus or minus a plus potential energy at x equal to plus or minus a. Now what is this value at any position? 500. So 500 equal to Ke at x equal to plus or minus a. What is that value? Now itself we came to know that 0 plus u at x equal to plus or minus, that is u at x equal to plus or minus a equal to 500 minus 0, that is 500 joules, right? In the same question, if I take u, question number 2, potential energy at x equal to 0 is 0, for example, right? 0. In that case, find all these factors, all the same factors, right? See question number 2. Now the question number 2. Second question. U at x equal to 0 equal to 0. See, potential energy of the particle at its main position is 0. In that case, find all the three questions. Question number A. What is that? The total kinetic energy at x equal to 0. So total mechanical energy at x equal to 0 equal to kinetic energy at x equal to 0 plus potential energy at x equal to 0. That is, what is the value here? 500 joules equal to K at x equal to 0 unknown, x equal to 0 unknown, plus U at x equal to 0 is what? 0 from data 0. That is Ke at x equal to 0 equal to 500 joules, right? Now question number B. Question number B. Kinetic energy at the either side of extreme positions. Naturally 0. Why? Because speed is 0. No need to solve. So kinetic energy at x equal to plus or minus a equal to 0 since speed at extreme positions 0. No choice. Speed is 0 at extreme position, right? So next question number C. Potential energy at x equal to plus or minus a means take total mechanical energy at the same position. Total mechanical energy equal to kinetic energy at x equal to plus or minus a plus potential energy at x equal to plus or minus a. That is, this is what? 500 joules equal to Ke at extreme position 0 plus U at extreme positions. Now what is the potential energy at extreme position? That is U at x equal to plus or minus a equal to 500 joules, right? So that's how one can find all the unknown quantities, making use of conservation principle, right? So total mechanical energy at any position during oscillation of the particle remains constant, even though potential energy as well as kinetic energy changes with the time or position. Total mechanical energy remains conserved. Okay friends, bye, see you in next video.